Okay, so now we've seen three kinds of accumulators. Context-preserving accumulators, results so far accumulators that help achieve tail recursion, and work list accumulators that help achieve tail recursion. And what we saw in the last example, count, was we used both a result so far accumulator and a work list accumulator to achieve tail recursive traversal of an arbitrary arity tree. This next problem is going to be the most subtle and wonderful problem we've done so far. You're going to love it, but it's not going to be that easy. Here we go. It's design a new function definition for same house as parent that is tail recursive. And it says you will need a work list accumulator. So here we're not doing a whole function design, we're just redoing the definition for our function we have. So even though this has been sitting down at the bottom of this file, I'm just going to copy it from cut it from here and move it right up here, because really all this is about is a new function definition for same house as parent. We're going to keep all the same tests and stuff. And so that we can see the test, I'll actually put the new one above the old one. So I'm going to comment out the old one. There it is. And we're going to start designing a new one. Now, it says it needs to be tail recursive, and I gave you this hint that you will need a work list accumulator. You know, I probably didn't need to give you that hint. Because if we start thinking about it right away, we know we're traversing an arbitrary arity tree. And we have to go everywhere in that tree. And it needs to be tail recursive. So that means we're going to need a work list accumulator, a to-do accumulator. So let's just make a note right at the beginning. I'm going to say, I'm not going to do it yet. I'm just going to say template from wizard plus work list accumulator. Now let's talk about that work list accumulator, that to-do list. Let's write the progression of those values as we go through the traversal. So we start just as we get to K, the work list is empty. By the time we get to H, the work list has I and J on it. By the time we get to C, the work list has D, I, and J on it. By the time we get to D, the work list has I and J on it. By the time we get to I, it has J on it. So each time we get to a wizard, we add all their children to the front of the work list. And then we take the first one off and keep going. So the work list always has kind of the rightmost part of the children at the front of it. And remember that in this tail recursive traversal, the way the function calling works is that there's a function call that goes fun for wizard on K. That leads to fun for LOW, which leads to fun for wizard on H, which leads to fun for LOW, which leads to fun for wizard on C. And then without producing a result right there, fun for wizard, remember it's all tail recursion, fun for wiz calls fun for LOW again, which leads to a call to fun for wiz on D. So what we can overlay over top of this arbitrary arity tree is in some sense the call structure. And if we kind of ignore the intermediate calls to fun for LOW, the call structure is like this. The call on K calls a call on H, which calls a call on C, which calls a call on D, which calls a call on I, J, E, F, B, G, A. That's the order of the traversal. That's the order of the function calls. So now we kind of understand what the work list accumulator has to look like. The original version of this was a lost context accumulator, right? Because we know that by the time we get to H, we need to know that its parent was in house G. And by the time we get to C, we need to know that its parent was in house S. And when we get to D, we need to know that the parent was in house S. And when we get to I, we need to know that the parent was in house G, and so on and so on. There's a little bit of a wrinkle to this problem. Was that the caller, the previous call to Fun for Whiz, called Fun for LOW with its house. But that worked in the non-tail recursive version. Because in that version, when you called Fun for Whiz with I, that was in a path coming from a call to Fun for Whiz with K. So the loss context accumulator worked. The call to Fun for Whiz with K provided as the value of parent house G, and that led through one call to Fun for LOW to the call on Fun for Whiz with I. But now, in a tail recursive traversal, the calling structure is quite different. If I just map out again the calls to Fun for Whiz, this is the line I see instead of this other path. So if I'm not careful, when we get to Fun for Whiz on I, we'll end up with the parent's house being H instead of G, because the most recent call to Fun for Whiz will have been on D, not on K. So how are we going to work that? How are we going to work that? Well, the answer is that the work list needs to be a little bit more complicated. The work list has to include, for each wizard on the work list, what its parent house is. Think about it. That's the moment in time in which we're all set up to do it. When we're at a call to Fun for Whiz on K, we're going to add three things to the work list. We're going to add H and I and J. But what we really need to do is add three pieces of compound information. We need to say, yeah, it's H with parent house G, and I with parent house G, and J with parent house G. And then when we're at Fun for Whiz with H, we add to the work list, hey, you know, it's C with parent house S, and D with parent house S. And then each time we take something off the work list, we'll know, hey, it's this wizard with this parent house. And you'll see that it'll work. By the time we get to I, we'll still know that the parent house is G. So this is really our picture of what the accumulator progression has to be. There's going to be a work list accumulator, but the work list accumulator is going to have this sort of compound information in it, where each entry on the work list is both a wizard to visit and what its parent house is. So in some sense, what's happening is the loss context accumulator is disappearing inside of the work list accumulator, because the context depends on when we added the entry to the work list. Turns out we've actually done the hard part. Now, based on everything you've learned in this course so far, I'm going to show you how to code this, and it's going to go quite quickly. Because what you're seeing here really is, because you can operate like a designer, you've solved the hard part of the problem by drawing this picture. I'll see you in the next video, and that's where we're going to code it up.